Every single second, there's a silent battle being waged for the integrity of your data. I mean, everything, the photos you take, the messages you send, it's all under this constant assault from the chaos of the physical world. And yet, it survives. So today, we're going to pull back the curtain on the incredible journey your data takes from just a perfect idea to a self-healing reality.
So where does this story even begin? Well, like a lot of things in computing, it starts with a beautifully simple idea. We have to go way back to the 17th century to a guy named Gottfried Leibniz. He came up with a system that could represent all numbers using just two symbols. That's it. This radical simplicity is what earned him the title the father of binary code. And man, did it lay the foundation for everything to come.
And that system is, of course, binary code. It's literally the universal language of our digital world. Every single video you stream, every website you visit, every mind-bendingly complex calculation your computer does, it all just boils down to an impossibly long but really simple sequence of ones and zeros. On or off. Yes or no. It's logic in its absolute purest form.
Okay, so we've got the language, but how do we get from these abstract ones and zeros to the actual physical electronics that power our lives? Well, before anything ever gets built, it first has to be designed in this perfect virtual world.
I mean, that's the multi-billion-dollar question, right? How do you translate that pure logic into a functioning blueprint? The answer is simulation. You build and test the entire circuit in a perfect virtual world before a single physical part is ever made.
And our ability to do this reliably is actually pretty new. It kind of started back in the 70s with a program called SPICE from UC Berkeley. But the real game changer for a lot of people was when tools like LT-SPICE came along in the late 90s, because they introduced these powerful graphical interfaces. And that took circuit design out of the realm of pure code and made it way more visual, way more intuitive.
And this, right here, is that translation in action. So on the left, you've got the engineer's view, this clean, graphical drawing of a circuit. Then, on the right, that's what the computer sees. The software just automatically converts that drawing into this detailed text file called a netlist, which basically describes every single component and every connection in a language the simulator can actually understand.
And this is just a brilliant illustration of how powerful that virtual world is. Honestly, the best way to think about it is like a flight simulator, but for electronics. In this space, every single component is perfect, every signal is crystal clear, and there's no such thing as interference. Engineers can test their designs billions of times, ironing out every single logical flaw before a single screw is turned. It's a world of pure, predictable logic.
But here's the thing. That perfect blueprint is about to face its greatest test. It has to leave the clean room of the simulation and try to survive the chaos of the real world, a world that is full of noise.
So what does happen when that perfectly logical design finally meets the messy, chaotic, and electrically noisy physical world? This right here is where the real challenge begins.
The villain in our story is something called noise. It's this constant, random electrical interference that's just all around us. It distorts clean signals, but its biggest threat is that it can cause a computer to misread a 1 as a 0 or a 0 as a 1. This is called a bit flip, and it's a huge, huge problem.
And yeah, it sounds small, right? A single bit. But one flipped bit can have absolutely catastrophic consequences. It can turn a vital piece of data into complete garbage, a stable program into a crashed one, or a crystal clear photo into a corrupted, glitchy file. We've all seen the results of this, even if we didn't know what was causing it.
So how in the world do we protect our data from this constant, invisible threat? Well, engineers came up with an incredibly clever solution. It wasn't a stronger wall, but a much smarter shield.
And here's the crucial insight. They realized they could never create a perfectly quiet, noise-free environment. That's pretty much impossible. So instead, they focused on creating a system so resilient that it could take the damage from the noise and just heal itself on the fly. This amazing system is called Error Correction Code, or ECC for short. The concept behind it is just genius. You add a tiny amount of extra, redundant information to your data. Think of it like a digital safety net. This extra information is the key, because it allows the system not just to know that an error happened, but to pinpoint exactly where it is and fix it automatically.
One of the most famous and widely used of these is the Hamming code. And the absolute best way to think of it is like an automatic, real-time spell checker for your binary data. It's just constantly watching for typos and fixing them instantly before they can ever cause a problem. Okay, I know, this looks a little technical, but the idea behind it is actually just a simple logic puzzle. So for every 4 bits of our actual data, we add these 3 extra parity bits. Think of them as tiny detectives. Each detective, P1, P2, and P4, is assigned to watch over a specific group of the other bits. For example, P1's job might be to make sure the number of 1s in its group is always an even number. If suddenly it's odd, it blows the whistle. But the real magic happens when we see which detectives raise an alarm.
So let's walk through it. Imagine a single bit somewhere in the data gets flipped by noise. Well, this is going to cause a totally unique combination of our little parity detectives to raise an alarm. For instance, maybe Detective P1 and P2 report a problem, but P4 says everything's fine. That specific pattern of failures, P1 and P2 failing while P4 is good, it acts like a coordinate on a map. It points directly to the one and only bit that could cause this exact problem. And once the system has that coordinate, it just flips the corrupted bit back. Done. Data healed. Instantly.
And listen, this isn't just some theory in a textbook. It is happening right now inside the technology we rely on the most. High-stakes systems, like the servers that run the internet, use special ECC RAM that is built on this very principle. It doesn't avoid errors, it's just constantly and silently fixing them, which is exactly why those systems can run for years and years without crashing.
So there you have it, the whole journey, from the pure, simple logic of binary code to the perfect virtual blueprints of circuit simulation, all the way to the creation of this resilient, self-healing digital shield that allows that perfect logic to survive in our messy, imperfect world.
It's really an incredible story of engineering and just pure ingenuity. And it makes you wonder, doesn't it, as you go about your day, what other invisible shields are out there silently working right now to protect our digital lives?